want to talk about using better shapes in the approximations. Better than rectangles, I mean. Check it out. Check it out. This is what it would look like if you use, say, rectangles. I just made up an example here using n equals 3. 3 rectangles on the right side. Remember, we are trying to approximate the area under the curve from here to here. This is this curved shape right there. These rectangles are kind of close to it, but this one is overhanging by a lot. This one is underhanging by a lot. Maybe it would be better if we could use a different type of shape. We can. Here's a great idea somebody had long ago. Instead of using rectangles where it goes up and then straight across, what if we were to look at both of these points and connect them with a straight line? That would look like this. I'm trying to draw the same picture again, but I'm not going to draw rectangles which have a flat, straight top. I'm going to make the top of each of these connect the 2 dots with a straight line. Now, to me, this looks like a much more accurate way of measuring the true area under the curve, all right? It's still not exactly going to match because the true area is curvy, but this is much better as an approximation. These are not rectangles anymore. What is the name of this shape? They look like that. You know the name of that shape? This actually is a trapezoid, right? Trapezoid, usually we draw this way. But that's a trapezoid too. Trapezoid just means it's like it has 4 sides. 2 are parallel, 2 are not parallel. So in this case, the 2 parallel sides are going vertically. The other 2 sides are not parallel. All right, these are trapezoids. And this is our first in the line of better shapes, all right? If you use trapezoids for your approximation, the approximation becomes much better. Of course, the trade-off is the area of a rectangle is really easy to do. What about the area of a trapezoid? It's quite a bit harder to do, right? Hopefully you know the area formula for a trapezoid. Maybe you probably learned it once when you were a kid. If you call this the width and this the height, it would be the average of the 2 heights times the width, which is more complicated than a rectangle. So if you're doing this with trapezoids, you get a more accurate result, but the formula is more complicated. But by some kind of magic, the formula, it's true, the formula is more complicated, but only very slightly more complicated. It turns out the formula is really still very easy to do, provided you can remember the formula. It's very easy though. I'm going to see if we can think this through and figure out what the formula should look like. If I were looking at a little piece of one of these guys and it looked like this. Now, if I was going to do the right-hand endpoint rectangles, it would be this big rectangle, right? If I was going to do the left endpoint, it would be this smaller rectangle going down to the bottom both times. And if I was going to do the trapezoid, it would be, we would have this kind of, cut it off diagonally like that. You don't have to be a genius to realize the trapezoid area is halfway between the left and right rectangles, isn't it? The left rectangle gets you only the small part. The right rectangle gets you this tall thing all the way up to the top. Cutting the difference in half, though, is what you'll get if you take the area of the trapezoid. So the trapezoid area is halfway between the left and right rectangles. Another way of saying halfway between, for numbers, that just means the average of those 2 numbers, right? The average of 2 numbers is what you get when it's halfway between. So that means the estimation using trapezoids of the whole area, adding together all the areas of the trapezoids, that is going to automatically be the average of if we use the left endpoints and if we use the right endpoints, because taking the average of all those different rectangles gives you the area of the trapezoids. This is the way that you can figure out the formula for the trapezoids. I will remind you of what is the average, or what is the formula for using the left endpoints. This is the formula for the estimation using rectangles on the left endpoints. We have b minus a over n, otherwise known as delta x, followed by a bunch of stuff. What we see here are the values of the function added together, where we begin with the one furthest to the left, and we go up to xn minus 1. This is to indicate when we're using the left endpoints, we don't actually use the last one. We go up to the second to last one, and then we stop there. So that's why this says xn minus 1. This means the next to the last x value in the subintervals. That's the left-hand endpoints. The right-hand endpoints look similar. The right-hand endpoints is the same, except instead of starting with the very first one, you start with the next one, and instead of ending with the second to last one, you end with actually the last point. All right, this is the left endpoints. This is the right endpoints. What does it look like when we take the average of these two formulas? What I'm going to do is add these together, and then divide by 2. Right? That's how you do the average of two things. Add them together. Multiply by a half. Can I say that? Instead of divide by 2, let's multiply by a half. This will be the average. You will see a lot of things can combine here. First of all, these all have b minus a over n. That can actually factor all the way out. And then what happens on the inside? These guys, they are almost the same. The only difference is this one has a x0, but that one doesn't. And this one has a xn, but that one doesn't. But otherwise, everything inside here being added together also appears over here being added together. So when I group all of these things together, we're going to get 2 of everything, except only 1 of the first one and only 1 of the last one. So it looks like f of x0 plus 2f of x1. That's because we get one of them from here and another one from here. Plus 2 of everything up to xn minus 1, the second to last one. And then finally we get only 1 of f of xn. All right? And so this is really the formula for the trapezoid approximation. But if you look up this in our book, they like to multiply the 1/2 through this whole thing. The effect is it will cancel all of these 2's, and it will end up putting an extra 1/2 on the front and on the end. So this is the formula put this in a box somewhere. This is the formula for the approximation of the area using trapezoids. For reasons that I don't entirely understand, this is referred to as the trapezoid rule. It's a rule, I guess. To me, I would call it the trapezoid formula. It doesn't really feel like a rule to me. This is just what you do if you want to find the approximation of the area using trapezoids. It's called the trapezoid rule. Who am I to argue with what people want to call this? This formula is all you gotta do. Provided you remember the formula, it's not hard at all to do this, right? It's kind of tedious. You gotta add a bunch of stuff up, but it's no more difficult than doing the rectangles on the left or on the right. Let's do an example. It says estimate the area under this function, f of x equals square root of x, from 0 to 4, using the trapezoid rule with n equals 6. I'm going to try and keep this right here because we're going to plug into this formula. You need to determine, really the only step that you need to do before plugging into the formula is just figure out what are all these x values that represent the little bitty points that you have to plug into the function. What are they? Well, same, just like we did last time. I'm going to make a simple chart of the interval. Now I'm realizing I copied this wrong. I meant to say from x equal 1 to x equal 4. Can I change that now? Sorry. Certainly you could do it, but they don't divide up very nicely in 6 pieces. This one divides up much better in 6 pieces. I can divide this, first of all, into 3 pieces by going just 1, 2, 3, 4. And then to get 6 pieces, I divide in half again. So this is 1.5. This is 2.5. This is 3.5. All right. And now these numbers, the 1, the 1.5, the 2, those are the numbers that I'm going to use in here. And that's really all there is to it. We just plug everything into the formula. Can I put it? I'll put it right under. All right. it's going to be b minus a over n, otherwise known as delta x. This is going to be 0.5 in this case, although you could just plug directly. Remember, b and a are these 2 points here. So it's going to be 4 minus 1 over 6. And I have just, you plug things into the formula. I put 1/2, and then f of the first point here would be f of 1 plus f of the next point is 1.5 plus plus all the way down to f of 3.5. And then finally plus 1/2 f of 4. All right, so the trapezoid rule says you put delta x on the outside, and then you just add, you use every value, but you got to put a 1/2 on the first one and a 1/2 on the last one. That's not so hard to remember, is it? This is not my final answer. I like to say, what does the f mean? The f refers to this function, which in this example is the square root. So my final answer I would write as 4 minus 1 over 6. I'm just going to replace every f with a square root sign. So 1/2 square root of 1 plus square root 1.5 plus etc. plus square root 3.5, and finally plus 1/2 square root of 4. All right, that's the answer. As usual, you could plug it into your calculator if you want to know what the answer is. I decided, just for the sake of impressing everybody, when I plugged this into my calculator, I got 4.6615. The true answer, so this is an estimation of the area under the curve. Now, we're going to learn later on next week or so how to find the true value of the area. So this is an estimation. The true area in this example, I wrote this down, is 4.6 repeating. This is quite accurate to that, right? The true area is 4.6 repeating. Very close to the trapezoidal estimation using n equals 6. This is much better than the rectangles would give you. All right. In the real world, there is, would you mind me being frank with you? I'll be frank with you. In the real world, you basically should never use the rectangles, because the trapezoid is much more accurate for hardly any extra work, right? You just have to remember, I got to put the 1/2 here and the 1/2 here. But really, there's no extra work to be done. It's the same stuff. You just do the formula slightly differently, and it becomes much more accurate. That's pretty awesome in my opinion. So in the real world, rectangles is not where it's at. The trapezoids are always better. But it turns out, I'm here to tell you, trapezoids are also not where it's at, because there's another very simple way to change the formula a little bit, which makes it even more accurate. And this is referred to as Simpsons Rule. Actually, if you look up the history, there's a guy named Simpson. Did not invent this rule. People named it after him because he sort of wrote about it and talked about it, but it wasn't his idea originally. This happens a lot in the history of mathematics and science. Things get named after the wrong person. But who am I to argue? Again, it's called Simpsons Rule, so I'm going to call it Simpsons Rule. The idea behind Simpsons Rule is to use a different kind of shape. Simpsons Rule is pretty crazy. In my opinion, the trapezoid rule is not so hard to come up with on your own. It's not a very weird idea to, instead of making straight bars across, you go diagonally across. This, though, is a weird idea. Simpsons Rule is based on taking intervals 2 at a time, first of all. You group them 2 at a time. And then, for this shape, instead of going straight across or going diagonally across like a trapezoid, you connect the 3 dots using a parabola. So in this one, maybe I'll draw it with my pink. For this one, maybe I use this pink parabola. So the shape that you get is sort of a rectangular thing, but the top of it has the shape of a parabola. And then this one, I might use a parabola that looks like that, all right? The fact that you're using a curvy thing makes this super accurate, all right? This curve will not exactly match the original function unless the original function is already a parabola, but it is quite close. And Simpson was able to figure out how to find the area of these parabolas. Now, I don't want to get into the details of that. I'm just going to tell us the formula. But you will notice the formula looks almost the same as the trapezoid rule. It just has a few different little things about it. But it is, again, much more accurate than the rectangles and even more accurate than the trapezoids. Here's the formula. This is the formula for Simpsons Rule. This, to me, is kind of a miracle that you can have such a weird idea, which is drawing the rectangular things but have parabolas on the top, taking the intervals 2 at a time. That is a weird idea, but it turns out when you work out all the details, it boils down to a formula that's almost the same as the trapezoid rule. It just has some coefficients in different places. First of all, there's a 3 there. And second of all, you don't have these 1/2s. In the trapezoid rule, you have a half here and a half here. Instead, in Simpsons Rule, you get alternating coefficients. There's no coefficient on the first one or the last one, but the ones in the middle, they alternate. 4, then 2, 4, then 2. So inside these dots, the coefficients go 4, 2, 4, 2, etc. All right, ending up with a 4. So how do you know it's going to end up with a 4? Actually, this works only, this is a slight limitation. This works only when the n is even, unfortunately. The reason is because Simpsons Rule is based on taking the intervals 2 at a time. So that's only going to work if you use an even number of intervals to begin with. Anyway, that's the formula for Simpsons Rule. You multiply by these 4s and 2s alternating and put the 3 out there, and suddenly, for basically no extra work, your approximation becomes much more accurate. In the real world, when people are doing this, they basically always use Simpsons Rule because you might as well, right? It's not any harder, really, than doing it the other ways, but it's quite a bit more accurate. You might wonder, isn't there something even better than Simpsons Rule? This can't possibly be the best ever. In fact, there are even better ones than Simpsons Rule, but they make the formula gets kind of increasingly weird, and for most purposes, it has been sort of decided as a rule of thumb that Simpsons Rule is good enough in the real world. Let's just try an example with Simpsons Rule. All right, estimate the area under square root of x from x equal 1 to x equal 4 using n equals 6 and Simpsons Rule. This is the same example we just did using the trapezoid. Do you remember the answer using the trapezoid? We got the area is approximately 4.66, what was it? 1.5 something, right? True area is the actual area is 4.6 repeating. Let's see how good we can get using Simpsons Rule, right? Simpsons Rule, if I'm right, it should be even more accurate than the trapezoid rule. Let's do it. Sorry, I had to erase the formula. We begin by drawing a little chart of the interval from 1 to 4 in this case, dividing into 6 pieces. It's the same as when we did the trapezoid rule with this thing, right? And I think we can just straight up plug into the formula now. These are the points. Sorry, I had to erase the formula. Hope you still got the formula on your paper. The formula for Simpsons Rule says b minus a over 3n. That would be 4 minus 1 over 3 times 6 on the outside. And then on the inside, I'm going to add together f of these values. The first one has no coefficient, so that's just f of 1. The next one has a coefficient of 4, f of 1.5, plus 2, f of 2, plus, and I'm going to alternate 4s and 2s. 4f of 2.5 plus 2f of 3 plus 4f of 3.5. And now I'm up at the last one, which has just a f of 4. All right? The second to last one will always have a 4 in it if you're doing it properly. If you end up on a 2 here, you messed it up somehow. And then the very last point gets no coefficient. All right? This is it. Let's just, I don't want to leave f's in my answer. I will write my answer like so. There it is. This is the answer. And if you want, as usual, you can plug this into your calculator. I don't know if you ever actually plug it into your calculator when I say that. I say that a lot. If you want, you can plug it into your calculator. This is a real pain to type into your calculator. But of course, in the real world, when people do this, and they do use Simpsons Rule a lot in the real world, they're using a computer to do it. So they're not pushing buttons on a calculator. The only people who use calculators are students in school, right? If in the real world, there's no reason to use a calculator. If you're doing serious computations, you use a serious computer. Anyway, I did this in my calculator. What I got, check it out, 4.66656, blah, blah, blah. All right? Even better than the trapezoid. Remember, the trapezoid answer was 4.66 something. It only matched up to 2 digits. Simpsons Rule, you get matching up to 3 digits past the decimal point. Pretty awesome. That's Simpsons Rule. State of the art.